Today we'll talk about decision tree learning inspired dynamic variable ordering for the weighted CSP. In this talk, we'll first talk about the weighted constraint satisfaction problem. Then we talk about branch and bound search and dynamic variable ordering. Then we talk about our decision tree learning inspired dynamic variable ordering. And then we talk about our experimental evaluation. Finally, we reach the conclusion. Branch and bound search has been the state-of-the-art paradigm for solving the WCSP, and the DVL dynamic variable ordering is a critical component of the branch and bound search. Our newly proposed DVL algorithms, which are inspired by decision tree learning, have shown superior performance in our preliminary experiments. First, let's talk about the weighted constraint satisfaction problem.
Used for medical and mechanical diagnostics, and it can also be used to solve energy minimization problems in computer vision. Formally, a weighted CSP is defined by n variables, and each variable has discrete value domain which it can take value from. It also has m weighted constraints. Each constraint specifies the weight for each combination of assignments of values to a subset of S of the variables. The problem is to find optimal assignment values such that the total weight can be minimized. The total weight is simply the summation of all weights in individual constraints. Since it is generalization of the CSP, it is naturally NP-hard. Here's an example of the WCSP. In this example, we have three variables in the WCSP. We have three unary constraints imposed on each of these variables, and we have three boundary constraints imposed on each pair of these three variables. The weight of each assignment of all the variables in each constraint is given in the tables. So here's an example to evaluate an assignment x1 equal to 0, x2 equal to 0, and x3 equal to 1. In this example, since x1 equal to 0, this constraint takes the weight of 0.7, and since x2 equal to 0, this constraint takes the weight of 0.3, and since x3 equal to 1, this constraint takes the weight of 1.0. Similarly, for the binary constraints, since x1 equal to 0 and x2 equal to 0, this constraint takes the weight of 0.5, and since x2 equal to 0 and x3 equal to 1, this constraint takes the weight of 1.3, and similarly this constraint takes the weight of 0.9, and we add up all these weights together, then we have the total weight for this assignment. So this is another example. This example we have the assignment of x1 equal to 1, x2 equal to 0, and x3 equal to 0. In this case, the total weight is 2.6, and this is the optimal solution that we explored by brute force. However, note that using brute force, it requires exponential time to find this optimal solution.
Now let's talk about branch and bound search and the dynamic variable ordering. So how does branch and bound search work in the context of WCSP? It does search by assigning value to one variable at a time until the optimal solution is found, and it does backtrack when it's needed. At each search node, there we have two important variables. One is the total weight of all constraints that are between all assigned variables. So when you have assigned a subset of variables, the total weight of the constraints between them is called WA. And the second variable is the total weight of the currently best solution, W dagger. So this is the one that we know from the beginning of the search history to the current node that what is the best solution. So at each search node, what does it do? It first chooses a variable and assign a value to it. So this is the part that dynamic variable ordering is important. Then it enforces local consistency, because very often local consistency can remove a lot of variables in the instance and make the search space much smaller. Then compute the WA, and then after compute WA, if all variables have been assigned and WA is smaller than the currently best solution, W dagger, then we update W dagger to be WA and backtrack. Otherwise, if not all variables have been assigned, then if WA is already worse than the currently best node solution, then we backtrack. There's no need to go down further. and after that we go back to 1, which is the next search node. Let's go through an example. Let's say there's a 3-variable WCSP instance. There are 2 constraints in it. The first constraint is between x1 and x2, and the second constraint is between x2 and x3. And the weights for correspond to each assignment of variables to each of the 2 variables are listed in this table. So in this table, x1 equals 0 and x2 equals 0 would have a weight of 400. x1 equals 0 and x2 equals 1 would have a weight of 300. x1 equals 1 and x2 equals 0 with a weight of 200, and x1 equals 1 and x2 equals 1 with a weight of 1. And similarly, there's also 4 weights for in constraint C2. Let's consider this search order, x1, x2, and x3. And we always assign 0 first, then assign value 1. The first search node is x1 equals 0. At this search node, since there's no unary constraint, then there's no constraint between all assigned variables, which is x1 alone. So we have WA equals 0. And because we haven't reached a complete assignment yet, we have W dagger equals infinity. Then we assign the next variable, x2 equals 0. Here we have 2 variables assigned, and there's 1 constraint between them. And we look at the table here, we have WA equals 400. And W dagger is still infinity because we still haven't reached a complete assignment yet. Then we do the next search step. We have x1 equals 0, x2 equals 0, and x3 equals 0. At this search node, we have all constraints involved. Now, we need to add these 2 numbers, 400 and number 1 here. So we have WA equals 401. Because this is a leaf, this is a complete assignment, we need to update W dagger because 401 is smaller than infinity. So W dagger is now updated to 401. And we go back, we backtrack to x2 equals 0 and make the next assignment of x3, which is x3 equals 1. So now we look at the table again. We have WA equals 402 and W dagger is 401. Because this is smaller than 402, we don't change that. And then we backtrack and we update the x2 and we do the same step here and then here. And eventually we found the optimal solution here. But since we don't know yet whether this is optimal, we still have to go 1 step further to try out the assignment of x1 equals 1, x2 equals 1, and x3 equals 1. So to find this optimal solution, we have visited 14 search nodes. Now let's consider a different search order. We still search from x1 to x3, but we always assign value 1 first and value 0. So here we have x1 equals 1. This is the first search node. Similar to the previous search order, we have WA equals 0 and W dagger is infinity. Then we have x1 equals 1, x2 equals 1, we have WA equals to 1. Then we have x1 equals 1, x2 equals 1, x3 equals 1. Here we have a first complete assignment. We have WA equals 5 and W dagger is updated to 5. Then we go to the next search node, which x1 equals 1, x2 equals 1, x3 equals 0. Here we have WA equals 3, and because 3 is smaller than 5, we update W dagger to 3. After that, we backtrack, and we go x1 equals 1 and x2 equals 0. Here we already found that WA is 200 and it's way larger than 3, so we don't have to try any value of W3. Then we go to the next search node, backtrack to x1 equals 0. Now x1, then we go down 1 level, x1 equals 0, x2 equals 1. Here WA is 300 and it's way larger than 3. So again, we don't have to try any assignment of x3. Then go to the next step, x1 equals 0, x2 equals 0, then WA is still larger than 3. So we don't have to try any assignment of x3. So in this search order, we found the optimal solution by visiting only 8 search nodes. This saves a lot of search nodes than the previous ordering. So the ordering of variables and their assignments can dramatically affects the efficiency of the algorithm. In this example, we only swapped the two assignments, but in reality, in many instances, reordering the variables could also have dramatic effects. Now let me introduce our decision tree learning inspired this dynamic variable ordering algorithm. Let me demonstrate the intuition behind our DV algorithm using this example. In this example, this is the CSP instance with 2 constraints and 3 variables. And roughly speaking, the weights in each constraint can be categorized into low weights, which are below 10, like 1, 2, 3, and higher weights, those above 100, like 102. I would like to use branch-bound search to find the optimal solution on this small WCSP instance. And here in this figure, we represent each search node as a rectangle. So this is the root rectangle where no variable has been assigned, and this is rectangle represent the situation where x1 has been assigned to 0. And this rectangle means that x2 has been assigned 1. At each search node, we use a circle to represent one possible assignment below that search node. So at this root search node, all 12 assignments are possible. That's why we have 12 circles here. And for x1 being assigned to 0, there are only 6 possible assignments left. So we have 6 circles in this rectangle. And we use a solid circle to represent an assignment that corresponds to a high total weights, which are those above 100. And we use an empty circle to represent assignments that correspond to low total weights, which are below 10. So, for example, x1 equals 0, x2 equals 0, and x3 equals 0 have a total weight of 2, which would be represented by an empty circle. And x1 equals 1, x2 equals 0, and x3 equals 0 would have a total weight of 204, would be represented by a solid circle. So if we align all these assignments at a search node, there will be 6 low weight assignment possible and 6 high weight assignment possible. So, but if we assign the first variable with the value, we would lead to different situations. For x1 equals 0, we would be in a situation where there are 5 possible low assignment and 1 possible high weight assignment. For x1 equals 1, there will be only 1 possible low weight assignment and 5 possible high weight assignment. So the intuition here is that we want to hit the low weight assignment as soon as possible. So here, if we choose x1 equals 0 as the first assignment, then we have 5 low weight assignments versus 1 high weight assignment, which would be very likely that we can hit 1 low weight assignment quickly, especially if this is a big instance, there are a lot of variables left. So the intuition here is want to hit this box quickly, but how do we know? The way to know this is by calculating how spread out the circles in a rectangle is. In other words, in the terminology in decision tree learning, this is called entropy. So we want to find low entropy boxes. We want to find the rectangles in which the circles are somewhat crowded to one type of value, to the low type value. So if we somewhat measure this and do a weighted average of all rectangles below 1 variable, we would have a good idea of which variable is the most favorable one. For example, here we would want to do x1 first because both of these 2 rectangles have circles that are pretty crowded to one type of value, so that we know that below x1, there's a good assignment. Of x2 and x3, because each rectangle behind below these two variables are evenly spreaded, so we would not have much much information. So that's why x1 is the most preferred as the first variable to assign. So what measurement can we use to measure the spread, how the circles in the rectangle are spread out? We can simply do this by sampling the assignments in the rectangle and computing either the standard deviation or the range of weights in the samples. The reason that we need to sample is because when the instance is large enough, the number of circles in a rectangle is exponentially large, and it's very inefficient to enumerate all the assignments. In fact, if you can enumerate all the assignments, you would have already finished the search. Now let's look at the experimental evaluation. We have 4 algorithms here. The first 2 have the measurement based on standard deviation and the weights of a range of weights in the samples, as we talked about in the previous 2 slides. And we have 2 additional ones, because if we sample, we would already have some total assignments corresponding to some weights. So we can actually directly use some of the weights as a bound during the search, use them as W dagger. And we have our competitors here. There's some traditional ones that are based on degree, domain size, weighted degree, and there are newer ones that are based on are more complicated, and they're based on some activities during the search environment, and so on. And we also added 4 inverse version of our algorithm. They're the same algorithm, except for that they're based on the reverse of the measurements that are used in our algorithms. Just interesting to see how they perform. So we used 2 set of benchmarks. The first one is from early 2016, the WSSP instance there. Because in our experiments, we implemented our algorithm using a very basic framework, just for the sake of fairness. There's no fancy stuff there. We limited the choice to at most 25 variables and domain size, no more than 6. And after imposing this limitation, there are only 6 instances satisfying this condition. Because there's just so few instances that would satisfy the condition, we also created random instances. So we add n variables and add a constraint between every 2 variables with probability, and we random assign weights from 1 to 100 in each of the constraint table. We range n from 12 to 20 to generate more instances. This is the experimental result for real-world instances. So this is a really small one, so everyone terminated pretty quickly. And these 2 are pretty difficult to solve, so often have been timed out for the 48 hours. For the instance in between, our new algorithm showed superior performance on all 3 instances, both in terms of search node and time. This is a result for random instances for n equals 20. The y-axis is the running time in logarithm scale, and the x-axis is the number of instances that each algorithm can solve within a given amount of running time. So here, because the y-axis in logarithm scale, a small gap can mean a lot of difference in linear scale. So here, both our SDR and R perform better than the others, and we didn't draw SDR bound and R bound because they look very similar to these SDR and R. Because we use a very basic framework for experimentation, we did not have the opportunity to test on instances with large number of variables. Here we analyze the trend of each algorithm when the number of variables increase from 12 to 20 as an indicator of what might be happening when number of variables is large. So there are two plots here. On the left, we have a plot with average running time as y-axis and number of variables as x-axis. So each cross here represents an algorithm's average running time on the random instances with a specific number of variables. So, for example, here, this cross will represent the algorithm SoC. Its running time on instances with number of variables equaling 16. So here, the lower the curve is, the more efficient the algorithm is. So here, the SDR and R are at the bottom of compared with other algorithms. And the trend, if we look closely, the slope is actually smaller than the other algorithms. So it might be, as we speculate, it might be the case that as n goes really large, the advantage of SDR and R would be much larger than the other algorithms. So because the y-axis is again in the logarithm scale, a tiny difference in the slope can lead to dramatic effects. And similarly, for the number of visit search nodes, we have a very similar trend. We have a large gap between SDR, R, and the rest of the algorithms. Here's the conclusion. Dynamic variable ordering algorithms can be critical in WCSP solving, and we created two new DVO algorithms inspired by decision tree learning. We demonstrate that they have more superior performance in our preliminary experiments. And in the future, we'd like to integrate our new DVO algorithms with state-of-the-art WCSP solvers and see how well they might be performing.